Hello and welcome to our 8th lecture. Today we're going to learn about linear independence. And before I'm going to give you the definition of linear independence, let us just recall what we've done last time. We were looking at these linear transformation gamma alpha, where alpha was a tuple V1 through Vn, and then we defined a linear transformation from Rn into V. V is a vector space where I took these vectors from, and defined this to be the following transformation where I just send a tuple lambda 1 through lambda n to the linear combination, given by the tuple alpha and lambda 1 through lambda n as coefficients. And then we saw that the span of V1 through Vn is equal to the whole vector space if and only if, well, this gamma alpha is surjective. So spanning had something to do with this linear transformation being surjective, and today we're going to investigate the question is, when is this linear transformation injective? So in order to do that, we're going to look at the definition of a tuple being linearly independent. So let's pull out a vector space V over R, and we're going to take an n tuple V1 through Vn from vectors in V. And then we say that this n tuple is linearly dependent. So that's the first thing we want to define here is, well, if there exists scalars, lambda 1 through lambda n in R, not all zero, so this is important here, such that the linear combination given by these scalars lambda I and the vectors vi is equal to 0. So meaning we have a non-trivial linear combination here that is equal to 0. By non-trivial, I mean that not all coefficients are equal to 0. As you can easily see, if all lambda i's are 0, well, then the left-hand side is obviously equal to 0 because each and every term is going to be equal to 0. So this means being linearly dependent, it means that you have like some linear combination that depends on each other, meaning that pretty much one element can be written as a linear combination of the others, but we'll get back to that later. And then being linear independent pretty much means you're not dependent. So otherwise we'll say that this tuple is linearly independent. And moreover, as a convention, we regard the empty tuple as linearly independent. So now let us first look at some examples. Number 1. These are certain vectors in a vector space you already saw in a homework assignment. So let us take 3 functions, v, f1, f2, f3. So those are functions, not linear transformation. Be defined as, well, we let the first one just be the constant 1 function. So this means that no matter what t is, this will always spit out 1. So the image of every element of R is equal to 1. Well, f2 of t, we let that be equal to cosine square of t. And then f3 of t, we let it to be equal the sine square of t. So these are elements of the vector space of all functions. Of f equal to, well, functions from R to R. And now I claim that f1, f2, f3 is linearly dependent. So f1, f2, f3 is linearly dependent. So I often shorten it to this, so lin dep. And why is that? Well, you could see that f2 plus f3 Well, this is what? This is cosine square of t plus sine square of t. Then if we remember well from our trigonometry, we'll know that this is always equal to 1. And well, this is equal to the constant 1 function f1. So this implies that f2 of t plus f3 of t plus minus f1 of t is equal to 0. Hence, they are linearly independent. However, if I only take 2 of them, let's say I'm taking f1, f2, these are linearly independent. So I write lin int. Okay. Secondly, now I'm claiming that the tuple, and I'm going to take a tuple in R3. This is one element, and I'm going to take 2, 0, 1 as the second element, and minus 1, 2, minus 1 as the third element of vectors in R to the 3 is linearly independent. Okay, and now I wonder, how do I even prove that? Yeah, up here in the first example, you show how you can see that something is linearly dependent by just giving an example of a linearly dependency. And then I claimed that this 2 tuple up there, f1, f2, is linearly independent, but I didn't really prove it. And so now comes the question, how do we prove that a tuple is linearly independent? And this will get us to our next proof strategy. So how is the general shape of a proof that vectors are linearly independent? And so what you do is, well, first you pick out scalars and let them be in a way that the linear combination given by the scalars and the vectors you have is equal to 0. Okay, and then the next step is, well, you have to show that this implies that all these scalars have to be equal to 0. So you have to find some mathematical arguments to show that no matter what they are, if they're in this way, meaning that this linear combination is equal to 0, then there's no other way than them being equal to 0. And then you can conclude that v1 through vn is linearly independent, yeah, because you've shown there's no linear dependent, no scalars witnessing they're linearly dependent. So what does it mean for us here? Okay. Well, let lambda 1, lambda 2, lambda 3, and r be such that, well, the linear combination of them with the elements in the tuple is equal to 0. So lambda 1 times 1 minus 1, 2, plus lambda 2, 2, 0, 1, plus lambda 3, minus 1, 1 is equal to 0, 0, 0. Okay, and now you might think something we've learned before, you have one equation here, it seems like, but you have 3 unknowns. So that would usually tell you, well, the system is underdetermined. But what you really have here is you have 3 equations, right? Because you have vectors in R3 here. These are vectors in R3. And so for each coordinate, you get a new linear equation. So this is true if and only if, well, let's look at the first coordinate here in green. So that means lambda 1 times 1 plus 2 lambda 2 minus lambda 3 is equal to 0. Now we look at the second coordinate. So we have here minus lambda 1, excuse me, plus 0 lambda 2 plus 2 lambda 3 equal to 0. And then the last one is 2 lambda 1 plus lambda 2 minus lambda 3 equal to 0. So this whole system. Great. And so now solving this, and I'm not going to do this in detail, but you do have to do that when you're proving that something is linearly independent. So solving the above linear system yields that lambda 1 equals lambda 2 equals lambda 3 is equal to 0. So we can conclude that they're linearly independent. Okay, so one more thing I want to say is here that, I'm not going to go into details here because solving linear equations should be something that you've learned in 33A and it's not really part of this class, so I assume that you already know it, so I don't want to go into details. And I do want to stress again, and I think I said this before, that you should really know how to solve linear systems. Yeah, what I mean by that is a lot of problems boil down to this, exactly like this. Yeah, so basically showing that elements in R to the n are linearly independent always boils down to solving a linear system. So, so you really need to have the skill of solving linear systems, 3x3 or 4x4 systems. So now let us kind of go into analyzing more what happens for linearly independent vectors. So suppose V is a vector space over R. And we take a tuple of vectors in that space. So n many vectors in V. Now note that the following holds. If we look at this linear combination here, so we assume that this is equal to 0. This is the same as saying that, so if and only if here, this element in R to the n, so the tuple given by the coefficients, this is, well, in the kernel of this map gamma alpha, and so I'm going to let this here be alpha. So why is that? Well, let's look what should be gamma alpha of lambda 1 through lambda n. Well, this is precisely by definition lambda 1 v1 plus all the way up to lambda n vn. Well, and then this by the left-hand side should be equal to 0. Yeah. And so you can go back and forth like this. So going on in this analysis, we can further notice that the fact that lambda 1 v1 plus lambda n vn is equal to 0 for, well, lambda 1 through lambda n equals 0 is related to the fact that 0 is always an element of the kernel of a linear transformation. Moreover, and so these are equivalences that we will use throughout. So observe that, well, this here is linearly independent if and only if, So what happens? Well, linearly independence will tell you that the only way you can add here lambda 1 through lambda n up to be equal to 0 is for lambda 1 through lambda n being equal to 0. So if this is the same as saying that this lambda 1 is in the kernel, then linearly independent should reflect that the only thing that is in the kernel is the 0 element. So that means that this is the kernel of gamma of v1 through vn is equal to, well, 0. Here by math, I mean the 0 in r to the n. And then this is the same by theorem 4.7 that gamma of v1 through vn is injective. And see, this kind of goes back to the question we had at the beginning of the class. Well, we ask, when is this precise map here, gamma v1 through vn, injective? And so, well, the answer is, well, it's injective precisely when the tuple is a linearly independent tuple. Okay. And so for the rest of this class, of this lecture, we'll point out some results about linear independent tuples. So the first one is kind of a tool. You can think of it in this way. It's not very interesting as a result itself, but it will help us later on to prove more complicated results. And what it says is that if you look at a one tuple, then saying that the one tuple is linearly dependent is the same as saying that the element inside is a 0 element. So the only way this could be linearly dependent is if it's 0. And you can see here this is an if and only if statement. So by what we've seen before, we have to prove both directions. But this is rather quickly here. So let's do this direction. So we assume that the one tuple is linearly dependent. So there is lambda in R such that, well, lambda times v is equal to 0. Thus, if we now look at v, well, v can be written as 1 times v. This can be written as lambda minus 1 lambda v. This now by another axiom 6, so this is axiom 5. This is multiplication in R. This is axiom 6, lambda minus 1 lambda v. This is lambda minus 1 times 0 by the assumption, which is right up there. And now this is equal to 0 by one of the consequences. Yeah, this is the result, the theorem right after the axioms of a vector space. So now, well, this overall shows that v is equal to 0. Let's go the other way. So suppose that v is equal to 0. Well, then 1 times v is equal to 1 times 0 is equal to 0. And so the one tuple is linearly dependent. So as I said, this is not a really deep statement at all. It's just a tool we want to have handy later on. Pretty much it's when we're going to do something by induction on the length of a tuple. And so what we want to say is that if we have length 1, then being linearly independent is the same as saying that the vector is non-zero. So let's go to the next result we want to prove. Theorem 5.11. So again, it's about linearly dependence and independence. So we have a vector space V here, and we're going to take n plus m many vectors out of that vector space for some natural numbers n and m, where potentially n or m could be 0. And so the first thing is basically saying that if you have a tuple that is linearly dependent, if I make this tuple longer, well, it will still be dependent. And let's think about it again. As we said before we actually want to prove statements, we always want to kind of convince ourselves that it should be true. So why should that be true? Well, if I already found a linear dependence amongst these Vn through Vn, well, then this will already witness one of this longer tuple because, well, I could just let all the later ones be 0. And then the second one is the other way around. If I start with the longer tuple and I suppose they're linearly independent, well, then the shorter tuple should be linearly independent. And it's pretty much a contrapositive of the first one, but we'll prove it separately and let us convince ourselves that this should be true. Well, if there's no linear dependence witnessed amongst this longer tuple, well, then I cannot possibly witness a linear dependence amongst the smaller tuple, right? Because again, as we argued before, a linear dependence amongst the smallers should induce a linear dependence amongst the biggers. So suppose your V1 through Vn is linearly dependent. Thus, there are lambda 1 through lambda n in R, not all 0, so this is important. I'm going to mark this, not all 0, such that lambda 1 V1 plus lambda n Vn is equal to 0. Okay, and so now we're going to artificially make this longer by just putting zeros in front of the other ones. So we keep this. We have 0 times Vn plus 1 plus all the way up to 0 times Vn plus m. Because this whole thing is just equal to 0. And so now this witness that they are linearly independent, as not all lambda 1 through lambda n are 0, the above witness that the longer tuple is linearly independent, linearly dependent. So this is the end of proof 1. Now let's do number 2. Now suppose that V1 through Vn plus m are linearly independent, and let lambda 1 through lambda n in R be such that, lambda 1 V1 all the way up to lambda n Vn is equal to 0. Yeah, so we're setting this up. What do we want to show? We want to show V1 through Vn are linearly independent. So I have to start with lambda 1 times V1 plus all the way up to lambda n Vn equal to 0. So please, I cannot say this often enough. Yeah. When you want to show something is linearly independent, you want to show that a certain tuple is linearly independent, then your first step, you should not think about anything else. You should not think about how do I actually want to prove it. Your first step has to be writing down this equation. Okay, so meaning you're going to take a linear combination in that tuple and set it equal to 0. The reason I'm saying this strongly is that I've seen it so many times before that students get sidetracked and they start with the wrong tuple. Often they start with the tuple they already know is linearly independent. So really, do yourself a favor and start with this. Why am I saying this? Because this leads you to the correct solution. And also, this already will give you at least 1 point. Yeah. So if you set up your proof correctly, you're already going to have 1 out of how many points there is. So even if you don't know how to continue, this will already give you partial credit. Okay, let's go on here. So now we have this linear combination and we know that this longer tuple is linearly independent. So we want to create a linear combination in that longer tuple that is equal to 0. And so basically we're doing the upper thing backwards. Then with this given lambda 1 through lambda n, we also have that this here is equal to 0. Okay, so this is now not an arbitrary linear combination in the longer tuple, but it is a linear combination that is equal to 0. We know already that certain coefficients are equal to 0, but not necessarily all of them. But well, now, knowing that this longer tuple is linearly independent, we now know that all of them have to be 0. Or in other words, the tuple v1 through vn is linearly independent. And this marks the end of proof of part 2. So now we're getting to the end of this lecture. So we have one more result we want to go over, and that is theorem 5.12 in the lecture notes. So let us given a vector space over R and an n tuple that is linearly independent. And then we take another element in the vector space Vn plus 1. And now we want to analyze the tuple where we adjoin Vn plus 1 to this linearly independent tuple V1 through Vn. And now we say this is linearly dependent if and only if, well, this element I attached is in the span of the ones before. So here you can see the first time we kind of relating linear dependence with the span. So now before I start the proof, again, we want to think about what does this mean? Well, why would this be true? Okay, so let's go from the second statement to the first. Well, if Vn plus 1 is in the span, well, this means that I can express Vn plus 1 as a linear combination of the right-hand side. And then by putting everything to one side of the equation, well, we're going to create a linear combination that is equal to 0. And as in that linear combination, the Vn plus 1 has a coefficient 1, this will be a non-trivial one. So if that was too fast, this will exactly what will be happening in the proof, so I will go over that. The other way around, well, if this is linear dependent, well, then I can have a non-trivial linear combination. And then, well, this is a little more tricky. In this case, we actually have to use linearly independence of the first tuple in order to get to the second. So we'll see that, but let me point out, if you listen carefully to what I argued first, meaning the implication to the span to linear dependence, you could see that by no time I actually referred to the fact that V1 through Vn is linearly independent. And this will tell you what? This will actually tell you that the implication from right to left does not depend on this assumption. But this assumption is necessary to go from left to right. And I will say something about that at the end. And well, this will also indicate that somewhat this implication from right to left is the easier one. So now, by definition of span, there are lambda 1 through lambda n such that, well, Vn plus 1 is equal to lambda 1 V1 plus all the way up to lambda n Vn. Yeah, we assumed Vn plus 1 is in the span. That means Vn plus 1 can be written as such a linear combination. So then let's put it all to one side. So we have Vn plus 1. And then we have plus minus lambda 1v1 plus all the way up to plus minus lambda nvn. So again, see how I don't write minus here, yeah? So I want to be careful. These are not minus signs because we didn't define minus on a vector space. Oops. And this will be equal to 0. Another thing you'll see is now, well, we don't really refer to the axioms anymore. So we kind of get more loose about how we structure our proofs, meaning from now we're getting more comfortable with the axioms, and we'll assume that the reader knows how to get from part 1 to part 2 here, even though we are using plenty of axioms to get from this equation, from the first equation to the second equation. Okay, well now, let me also add here a 1 first, yeah, just to make it clear. So now as 1 is different from 0, this witness that this tuple is not linearly, this witness that this tuple is linearly dependent. So here note what I said before, the assumption that v1 through vn is linearly independent is not necessary for this direction. Okay, so now let's go to the other direction. So assume that v1 through vn plus 1 is linearly dependent. E dot there are lambda 1 through lambda n and lambda n plus 1 in R, not all 0, such that lambda 1 v1 plus all the way up to lambda, let's say, n vn plus lambda n plus 1 vn plus 1 is equal to 0. Okay, I'm gonna scroll all the way up, so we're on the second part here. So now what would be the idea? Well, what I want to do here is, and I'm going to erase this, but I'm just going to give you some ideas. Well, we kind of want to put this on the right-hand side here, right? And express vn plus 1 as a linear combination of the ones before. So naively, what would I want to do? Well, I put this whole thing to the right-hand side. So I would get here, well, lambda n plus 1 minus vn plus 1, which is equal to the whole right-hand side, yeah? And then, well, I want to get here a 1, right? Because in order for vn plus 1 to be in the span, I didn't say that a scalar multiple of vn plus 1 is expressible as a linear combination, but that vn plus 1 is a linear combination. So what I want to do is, well, this vn plus 1, right, I would kind of want to multiply this right-hand side by 1 over minus lambda n plus 1 times what I had before. And now, well, you might see the problematic here is that, well, this should be different from 0, otherwise I can't do that. Okay, well, I did have that not all are equal to 0. But it doesn't mean that not like all of them are not 0, yeah? It could be that just lambda 1 is not 0, but lambda n plus 1 could potentially be 0. So now we have to argue that this lambda n plus 1 cannot be 0. So this is the first task we have to do here. Let me go backwards. This is a long backwards. Okay, oops, forward. Okay. So now claim here lambda n plus 1 is not 0. suppose towards a contradiction that it is 0. So we're using the contradiction method to prove this. And let's refer to this equation here as star. Then star simplifies to this shorter linear combination being equal to 0, and then, but you still have this condition that not all of the lambda i's could be equal to 0. Since lambda n plus 1 is equal to 0, some of the other ones doesn't have to be. Well, but now, and this is precisely the point where this is precisely the point where the fact that that v1 through vn is linearly independent comes into play. So as v1 through vn is linearly independent, this leads to a contradiction. And so this establishes the claim. Establishes the claim. And then now I can repeat what I tried to do before. Then star is equivalent to, so I'm going to fast track this. Minus 1. Sorry, there's no minus sign here, sorry. So like this. Plus all the way up to plus 1 over minus lambda n plus 1 lambda n vn. And this implies, and this is actually vn plus 1, that vn plus 1 is actually in the span of v1 through vn. And this finishes our proof. And this will finish the recorded lecture for today. I will go over an example where this theorem fails whenever v1 through vn is not linearly independent. And I'll do that in the live lecture on Friday. I hope to see you there. Bye-bye.